Dear students, welcome to this third part of KCET Belaku classes. Today, I will solve a few very important questions on current electricity chapter. Come on, let us begin with the question number 7.
A copper wire of length 1 meter and uniform cross-sectional area 5 into 10 to the power of minus 7 meter square carries current of 1 ampere. Assuming there are 8 into 10 to the power of 28 free electrons per meter cube in copper, how long will an electron take to drift from one end of wire to the other? The options given here are option A 0.8 into 10 to the power of 3 seconds, option B 1.6 into 10 to the power of 3 seconds, option C 3.2 into 10 to the power of 3 seconds, and option D is 6.4 into 10 to the power of 3 seconds. What it is given is a copper wire of length 1 meter having a uniform cross sectional area 5 into 10 to the power of minus 7 meter square. It is carrying a current of 1 ampere. And out of the number of electrons given, free electrons given here, 8 into 10 to the power of 28 electrons, and how much time does one electron take to drift from this end to this end, that we need to calculate. Means the time taken by one electron to drift from one end to other end of the copper wire. So here T you have to calculate, and L is given 1 meter, A is given, and I is given, N is given. We know the formula that T is equal to L by Vd, where L is the length and Vd is the drift velocity. And also drift velocity is equal to, you know that this is equal to I by NEA. So therefore the time taken is equal to, so you can write this one as L into NEA by I. When you put this value of Vd here, you will get this formula. Now putting all the values given here, you can get the value of time. So this is equal to L is given as 1 meter, 1 into N is 8 into 10 to the power of 28, and the area of cross section is given as 5 into 10 to the power of minus 7, and the value of I is 1 ampere. So when you simplify this one, for T is equal to 6.4 into 10 to the power of 3 seconds. So this is the answer. Therefore the option is D. Now we shall move on to the question number 8. Consider an electric conductor connected across a potential difference of V volt. Let delta Q be a small charge moving through it in time delta t. If I is the electric current through it, first one, the kinetic energy of charge increases by a factor I into V into delta t. Second one, the electric potential energy of a charge decreases by the factor I into V into delta t. Third one is the thermal energy of the conductor increases by I into V into delta t. Then the correct statement or statements is or are option A first one, option B first and second, option C first and third, option D second and third. Here we find two possibilities. One is when charges move with collisions through this conductor, as the charge flow is from higher to lower potential, its potential energy decreases when the kinetic energy increases,
And kinetic energy is transferred to the conductor,
which increases the thermal energy because of these collisions. So therefore with the possibility 1, we can find the answer as D. With possibility 1, that is for this one answer is D. That is, the kinetic energy of a charge increases by a factor I into V into delta T, and the third option is the thermal energy of the conductor increases by a factor I into V into delta T. And the second option, second possibility is when charges move without collisions, through conductor. So what you find here, when the charges move without collisions, that time we can see there is an increase in kinetic energy. Thereby, to maintain the law of conservation of energy, so the potential energy decreases by the same factor. That means what?
The statements 1 and 2 are the correct statements. Therefore, answer for the second possibility is B.
So therefore here answers are it may be the option B or it may be option D. Next question is, a strong magnetic field is applied on a stationary electron. Then the electron moves in all direction of the field. Option B, moves in the opposite direction of the field. Option C, remains stationary. And option D is starts spinning. If this is a stationary charge, and when you apply a strong magnetic field for this charge, since the charge is stationary, this application of the magnetic field is not going to affect this stationary charge. You know that, but the same when the charge is moving with a certain velocity, that time it experiences a force. For the stationary charge, the applied magnetic field is not going to affect in any manner. Therefore, the answer is C. The charge remains stationary. And we shall move on to the next question. Question number 10. Two parallel wires in free space are 10 centimeter apart and each carries a current of 10 ampere in the same direction. The force exerted by one wire on the other, that is per unit length, is option A 2 into 10 to the power of minus 4 Newton per meter, so that force is attractive, and option B 2 into 10 to the power of minus 7 Newton per meter, and the force is attractive. Option C 2 into 10 to the power of minus 4 Newton per meter, the force is repulsive in nature, and option D 2 into 10 to the power of minus 7 Newton per meter, and the force is repulsive in nature. Students, here the two wires of length L are given. They are separated by a distance of 10 centimeter. So both are carrying the same amount of current here. So this also carrying, I1 is also 10 ampere and I2 through this another wire is also 10 ampere. If they are carrying the same amount of current, then they will exert the same amount of force on each other. So that force you can take it as F. And this is the distance D. We know that force is equal to mu naught upon 4 pi into 2 into I1 I2 into L by D. Now we need to calculate the force per unit length. That means what? Or you can write this one as F by L. You can take this L here only, or you can divide both sides by L. This is the force per unit length, and the equation becomes mu naught upon 4 pi into 2 I1 into I2 by D. Here the value of mu naught upon 4 pi is equal to 10 to the power of minus 7 is a constant. Now putting the values of I1 and I2 and the value of D and this constant, we get this is equal to, so the value of mu naught upon 4 pi is 10 to the power of minus 7 into 2 into I1 is 10 ampere into I2 is also 10 ampere by distance given is 10 centimeter, that you can convert it into meter. 10 centimeter into meter, 10 into 10 to the power of minus 2. So therefore the force per unit length of the wire is equal to, when you simplify this one, you will get a 2 into 10 to the power of minus 4 Newton per meter. Force is attractive. Because the direction of the current in both the wires is in the same direction, therefore force is always attractive. So this is the answer. So therefore the option is A. The next question is, a toroid with the thick windings of n turns has inner and outer radii R1 and R2 respectively. If it carries a certain steady current I, the variation of magnetic field due to the toroid with radial distance is correctly graphed in. So here 4 options are given. Option A is graphed like this, and option B graph is this one, and option C graph is this one, and option D graph is this one. Students, here toroid has the n number of turns, so n turns here. This is the toroid. So the inner radius of this toroid is taken as R1 and outer radius is R2, and the radial distance, the average R1 and R2 is taken as R. And here if R is less than R1, then the magnetic field is equal to 0 inside. Here magnetic field in is equal to 0. For R greater than R1 and R2 means at this position, here this particular point, this R is, so greater than R1 and less than R2. For here the magnetic field B is always constant. That is, B is equal to constant here. B is equal to constant. And outside this toroid also we find B out also 0. The magnetic field outside the toroid also 0. And now we know that we have to find the variation of magnetic field due to the toroid with the radial distance. So R is the radial distance here, and we know that the magnetic field B of a toroid is given by mu naught Ni n into I, where I is the current and n here it is n by 2 pi R, where capital N is the number of turns of the toroid and R is the radial distance. And also this R is taken as the mean of the average of this R1 and R2. R is equal to R1 plus R2 by 2. Therefore the magnetic field, variation of magnetic field due to the toroid with a radial distance is given by B is equal to mu naught, where n is n by 2 pi R, that is known as n into I by 2 pi into, where R is here R1 plus R2 by 2. So this 2 cancels. What remains is B is equal to mu naught Ni by pi into R1 plus R2. Now you can see here in each graph, so where this x-axis is representing the radial distance and the y-axis is representing the variation of magnetic field. And here, so it depends on, so just you can check out the each what graph there, and where B is found to be mu naught Ni by pi into R1 and R2, R1 plus R2. That is, so when you check this one, we won't find any value of this B here in this graph, therefore this is not the option, this is not the answer. And option B also, where we find the different values of B, so we can, this cannot also be the answer. And option C, so here also we find the different the values of B, so this is not also a answer. And option D, you can see here R1 and R2, and this one mu naught Ni by pi into R1 plus R2. So this is the right answer. Answer is D.
Dear students, I hope that you have understood the complete solutions in this part 3 KCET Belaku classes. Friends, place your questions of doubts if any in the comment box. And don't forget to subscribe this channel and attend all the Belaku classes. Thank you.